All right, so it's time, and thank you for having me for the second day for multigrid methods in scientific computing. And what was, in my own personal belief, was to be advances and challenges, and a primer and a lecture on that. However, there is a great book beautifully written by Northcote Parkinson. The title of the book, it's satire. The title of the book is Parkinson's Law, and the first opening sentence is, "Work expands so as to fill the time allotted for its completion." It's satire on the British administrative works as they go on with British government and army and navy. But what doesn't mention, however, is sometimes it can go well beyond the time allotted for its completion. So basically, the time allotted for these series of lectures was 2 lectures, but it seems to me that it might go on to 4 or possibly 5 lectures. So I introduced partial differential equations as a recap in the last lecture. And we spoke about the different kinds of PDEs in science that we have, the scalar PDEs, not the coupled ones. We briefly spoke about the Schrodinger's equation and how a Fourier transform of it leads to the time-dependent stationary equation, which is a parabolic equation. We spoke about a few elliptic equations, and we just saw a glimpse of the wave equation. We discussed discretization methods, what was meant by big O of h square, kind of truncation errors when you truncate Taylor's expansion around certain particular points for a derivative. And we saw how could we construct the matrix on the right side. Then we checked out that all the classical stationary iterative methods, such as omega Jacobi, Gauss-Seidel, etc., they don't really work well with these kind of system of linear equations coming out of a discretized partial differential equation. The reason was shown to be that you could basically divide the error or decompose the error into 2 sets of basis vectors in which it could be basically expanded. And these classical stationary methods were only good at removing the high frequency components, and the low frequency persistent components were the one that caused these methods to stall. And then we came up with a design and a framework whereby we can put together a 2-level iterative method, so that the high frequency components could be eliminated on the fine level and the low frequency components could be taken care of at the low level or at the cost level. And then I showed you an implementation of it in MATLAB. We saw how it compares with the classical methods such as omega Jacobi, Gauss-Seidel, how those methods stall, and how really fine problems with very small h, how it could still be dealt with multigrid, and it was 1 order of magnitude reduction in the residual norm at each level, which caused it. So if you had a tolerance that an approximate solution was acceptable up to, let's say, 10 to the power negative 10, then this could be achieved of relative residual, then this could be achieved in, say, 10 iterations of multigrid cycle. And it wouldn't matter if the discretization was coarse or if the discretization was fine. It still worked in a pretty much mesh independent way. What, however, I had thought of presenting and could not present in the last class was an analysis of these methods. So from elementary numerical analysis, we all know that iterative linear solvers were convergent if the spectral radii were less than 1. But how actually, so this basic principle still rules. But this basic principle is kind of non-trivial to disentangle in the case where you have an iterative method that works across scales. And today we are going to just see how we are going to handle that. Okay. In the next class, so this was meant to be an advances and challenges lecture on multigrid, where we have, where do we currently stand with the project, say that Zulfikar is dealing, or Shahid Ashraf is dealing, or Shanila has lined up. But it would take at least this lecture and another lecture. Today is a rigorous Fourier analysis of the two-grid methods, and I'd end this lecture as soon as it's done. The next one's supposed to be local Fourier analysis, which has a wider scope of analyzing different multigrid methods and cycles. As soon as we do that, we would have to see the amount of work it takes to do it. We really need to be sure of that it's not just implementation and digital architecture which is causing this method to converge rapidly, and that indeed the amount of work needed reduces as well. So after we've built up enough theory, we discuss H-ellipticity. In the fourth lecture, we'd see why is H-ellipticity a required condition, why is H-ellipticity, why does it get hampered with certain interesting problems that we have in within a Navier-Stokes solve, say, of computational fluid dynamics, and how do we overcome by different strategies and build a multigrid method that works nicely. And then finally, before I start with the advances and challenges lecture, there would be a short primer on what is meant by preconditioning a Krylov method, Krylov subspace method by multigrid. So that would mark the end of the introduction to multigrid. I apologize for this underestimate at the outset that I made of wrapping up everything in 2 2-hour lectures, but I believe it would overflow on to a few more lectures. So bear with me with that. Okay, so now let's start with a small outline of what we are going to talk today. We'd see what is meant by two-grid convergence, and one of the questions raised by Dr. Babar in the last lecture was, fine, you showed it that it works, but it looks like magic. How does everything work? How could we be sure that this would actually converge to the solution? So this is something that we need to see today. The basic outline, as I've just said in a few minutes ago, is exactly the same. A method, an iterative method for aiming for a linear solve would converge if its spectral radius was less than 1, as simple as that. Okay. So we'd see that we have to go towards two-grid rigorous Fourier analysis, and then with apologetically, I'll give you a few minutes short linear algebra primer on invariant subspaces. Once we are done with that, we would go to rigorous Fourier analysis preliminaries, then smoothing, rigorous Fourier analysis only for omega Jacobi, then two-grid rigorous Fourier analysis. Finally, we'll see how could we construct the spectral radii of the two-grid error iteration operator. Okay, this is a short recap of what the two-grid algorithm was. So the two-grid algorithm has a pre-smoothing step, which means that you have some smoother. The representation in this algorithm is slightly different from what I presented earlier. So this is the error iteration operator of the smoothing method. It encapsulates any method, any classical iterative method that works on a single level, okay, and which works on all the grid, which means that it encapsulates Jacobi, omega Jacobi, Gauss-Seidel. It incorporates successive over-relaxation. It incorporates SOR, SOR is successive over-relaxation, AOR, accelerated over-relaxation, symmetric successive over-relaxation, and any one-grid method. Okay. It can also incorporate, though I have not incorporated it in this lecture, red-black Gauss-Seidel or red-black omega Jacobi kind of methods, which basically partition the grid into two structures of grid points and iterate in 2 half sweeps instead of 1 full sweep. Okay, so much for SH. So that SH is the error iteration operator of the smoother. A new 1 written in the superscript simply means that number of iterations have gone by before you could call that you're 1/3 of the way. So the entire thing that helps you take this as the input, this one as the initial guess, and create this as the output of the first cycle is in 3 steps. Those 3 major steps are pre-smoothing, course grid correction, and post-smoothing. And course grid correction, to make it simplified, has a few sub-steps that I've jotted down here. Okay, next comes course grid correction. We compute the residual at the fine grid. The residual is the right-hand side minus the system matrix times what estimate you obtained from the pre-smoothing step. Then you average the fine grid residual to the coarser grid. You call that procedure restriction. And we represent it by R sub 2h now. And this is the restriction operator, IH sub 2h. So in the previous algorithm, I represented this by the matrix R, but this is the restriction operator. These are the same thing. R is the matrix, this is the operator. There's no big difference between the two. These are literally the same thing. We just say it's restriction from H grid to 2H grid. And similarly, restriction and prolongation would be I2H to H. This would be prolongation or interpolation. Interpolation is also a familiar concept. So we formulate A2H, which is the coarse grid operator. We could formulate it fundamentally using 2 different conditions. One is the DCG, the rediscretization of the partial differential equation using the same boundary condition techniques on the coarser grid. The other is by using a variational technique, which is known as the Galerkin coarse grid operator. So we formulate A2H. That's a short story.
Can you remind this AH is the matrix defining your problem?
Yes, on the fine grid. And for now, you could, in a simplified way, assume that A2H is the matrix representing the problem on the coarse grid, using the same conditions that you applied on the fine grid. Even though you could basically put out a fierce debate that the original equation was on the principal unknown u, whereas the coarser equation is on the error, not on the principal unknown. But for certain reasons, the two correspond in the way that whatever is eliminated on the fine grid gets eliminated on the fine grid, whatever is left out at the fine grid is taken care of on the coarse grid. For now, for the purpose of this exact lecture, I am not going through a recursive V-cycle multigrid solve, which means that I just have 2 levels in the entire sequence, a fine level and a coarse level. And on the coarse level, after I formulate A2H, I just say that E2H is a direct solve of the error equation on the coarse grid. Direct solve means an exact solve. Exact solve doesn't always have to mean that you invert the matrix in the traditional way. That's never advisable with the kind of binary computing, floating point computations that we have. What we rather do is smart, direct, exact solves using certain categories of LU decompositions, like the Kuleski decomposition, Kraut's LU decomposition, Doolittle's, and there are many others. Okay, so we have in most implementations of numerical linear algebra, we have usually an overloaded operator, which when indulged, looks at the matrix, looks is a word, looks at the matrix, sees if there is a structure in the matrix that could readily be exploited to lessen the amount of work needed for an exact solve, invokes that, and gets you the exact solution.
So this inversion, this will have much less precision than what you are trying to build?
No. So my equation.
If you can just like do this, then I don't understand.
So A2H, U2H is E2H is equal to R2H is the coarse grid equation. Okay. So the degrees of freedom is much less on this scale compared to the fine scale. And the presumption for now for simplicity's sake is that let's assume that we have a computational architecture that cannot invert this equation because of the scale involved, but can invert this equation exactly. Yeah, this has lesser variables. It's a less heavier system.
So their decisions are comparable.
Yep. Okay. Yep. So E2H in this scenario is simply A2H inverse R2H. Okay. Now we interpolate E2H to the fine grid. That would not give us the exact error on the fine grid. If we had that, the entire story would be shortened. We just have the pre-smoothing estimate. If we had some magic of getting to EH instead of in place of what we do get by interpolating the coarse grid error, we would make short work of it in one iteration. But we unfortunately can't do it. Okay? So what happens? We interpolate upon E2H in order to get an approximation of the fine grid error. Then we add that fine grid error to the estimate from pre-smoothing, first step. We add that, we say we are now 2/3 of the way, and then we use the smoother, new 2 times on this, and then call the result an iterate of the 2-grid algorithm. Okay, so this is a basic recap. We've gone through it in the last bit of the last lecture. And now we'd see how to analyze this. All right, so the first thing is to build an operator. Okay, when I say an operator, this is an operator. This is a linear transformation. This is also a linear transformation. In the loose way of saying, we often say this is the restriction operator and the prolongation operator, though per se they are not operators because operators are from same dimensional space to the same dimensional space. So there are other linear transformation, but if I do make this mistake of calling, or the sin of calling a linear transformation as an operator in this context, you should know that I mean a matrix that is multiplying to a column vector and transforming things into another space. Okay, so I do have a couple of operators here. So imagine that in case of this one, UH1, what I do is I say, fine, I have SH nu2. Now instead of writing UH2 by 3, I plug this in. I say this is UH1 by 3 plus EH, and then instead of this UH1 by 3, I plug that in, and I say, fine, I have SH nu1 UH0 plus some vector CH, and this is SH nu2, and then I use this representation. I say this is this times this, and then instead of this, I say this is this times this. Instead of saying this, I retrace all the steps. So I would construct basically a matrix operator that stands for the 2-grid iterative step. And I do it precisely in this way, only that I'd spare you this agony of going through all of it and just show you what we get. I represent it by M sub H super 2H. It is, first of all, so if I had an error vector here, I want to see how the error would evolve under MH to 2H. I would first subject it to pre-smoothing, then to this coarse grid correction operator. After that, I would subject it to post-smoothing. This is how it's going. In literature, the coarse grid correction operator is a divergent operator in its own spite. So it is given the name K sub H to 2H. Whatever you see in the braces in the first line is this one. This is known as the coarse grid correction operator. There are a few observations related to this. The 2-grid method, first of all, is a stationary method. So what did I say about classical stationary methods in the last section, in the last class? a method was stationary or it was dubbed stationary if it has something like this. Some matrix, let's call it B, some matrix times this plus some other vector. So if from iteration to iteration this matrix B ain't changing, then we call this a classical stationary method. And as we can see already, the observation is that the two-grid method is a stationary method. It's convergent if the spectral radius of it is less than 1, whatever that means. I haven't yet finally or in a refined way defined yet what is meant by its spectral radius, but spectral radius has more or less the same connotation, same meaning, what you already know, as in some way obtaining the largest effective absolute eigenvalue of the operator. Defining this needs a bit of work, which is easy. I mean, it's a bit lengthy, but it's easy. There's no great difficult science in it. Fourier sine modes are not eigenmodes of either the cos-grid correction operator or the two-grid operator MH2 2H. Do you have any questions so far? Okay, so where we're going, we're headed towards a two-grid rigorous Fourier analysis. We take a short detour from this and just be students of linear algebra for a bit. So a short linear algebra primer first. So imagine that, so this is R super 16. It's not just R. It's a 16-dimensional Euclidean space, simple. So let Vi belong to R16 such that Vi are linearly independent. And R16 is a span of this ordered basis written out like this. So each vector, I've named those vectors V1 to V16, but I have taken the liberty of lining them up in a peculiar order. Okay, and when we are doing the analysis of the multigrid method, we would understand why this was necessary to show. Okay, so R16, since they're linearly independent, since each one of them belongs to R16 and the 16 in number, they form an alternate basis for R16. So we now say that the first four, V1, V5, V9, V13, their span is S1. S2 is the span of the next four, S3 is the span of yet the third four, and S4 the span of the fourth four. Okay, so consider spaces Si constituted as span of four basis vectors of R16 clubbed together owing to a certain rule that we don't speak about it just yet. Okay, any questions so far? So Si, these spaces, what kind of constitution they have? They're four-dimensional spaces, first of all, because their basis has just four vectors. Each vector belongs to that Euclidean space that we have. In this example, R16, this is a simple example. So believe that there is some arbitrary vector that I call E that belongs to R16. Then I can obviously, since R16 has to be a direct sum of S1, S2, S3, and S4, I believe that this bit is well understood, or does it need more elaboration? Cool. Okay, so R16, since it's a direct sum, any vector belonging to R16 could be written down in these four components, where each of these respective components belong to a subspace. Okay, now let A and C be linear operators on R16 such that these linearly independent vectors are eigenvectors of C, but not of A. They're not eigenvectors of A. But A and C are still linear operators on R16. However, 4-dimensional subspaces Si are invariant under A, which means whenever A acts on a vector belonging to a particular such subspace, A times that arbitrary vector from that subspace stays to be in that subspace. It cannot flow out of it and be a vector in some other subspace. Okay, so this is a very simple, clear, I hope so, clear definition of invariance. So we would like to check the amplification. Amplification simply means A times E of an arbitrary E belonging to R16 under a linear transformation AC. Okay, now we say, fine, for a moment, let xi be a vector that belongs to Si, and let x be the sum of 4 constituent parts, so that we may want to write x1 as eta1 times v1 plus eta2 times v5 plus eta3 times v9 plus eta4 times yeah, again a typo, I believe. Apologies for this. So this is a v9, v5, v9, and v13. So I have to make a correction here. Apologies for that. All right. So A times, when A, you could call it A times, or you could just say when A is applied to v1, what do we get? We get an expansion of the basis vectors of the space in which v1 lives. So v1 lives in S1, and S1 is the span of v1, v5, v9, and v13. So when A is applied to v1, you get a linear combination of the basis vectors. This is that linear combination. When A applies on v5, this is what you get. The constants merely change. This is a simple representation. So what we see is that when A applies just to x1, one of the constituents, what we get is eta1 times AV1 plus eta2 times AV5 plus eta3 times AV9 plus eta4 times AV13. And we really need to have a proper representation or a lineup of these vectors. Now, what we do have is this, which looks like a row vector, but it's not a row vector. What is it in fact? What is it in fact? Yes, Salman Sahab? Yeah, so this one, in this example, this is a 16 cross 4 matrix. Okay, each one of this is a column vector in R16. Okay. So when you multiply AX1, then you have plus AX2, because you're analyzing the amplification of X, which is a sum X1 plus X2 plus X3 plus X4. We've already seen how it goes if I just apply this to the basis vectors. So if I now apply it on this, I have to work that out, and it happens that I get this matrix times this 4 cross 4 matrix times the amount of each basis vector I had in the initial representation, just the amount. And this is only for A times x1. Any clue how would it go if I had A times x instead? A short quiz. Yeah? You remember it? No? Okay, so if I have A times x, naturally this becomes A times x1 plus x2 plus x3 plus x4. I have these 4. And then what I get here is a 16 cross 16 matrix, which is block diagonal, and the diagonal blocks are 4 cross 4. And this is how the diagonal blocks look. it is that those same alphas but transposed, if you look closely. Yes, so understanding this representation is fundamental to understanding how we analyze multigrid methods. If there's anything that you need in terms of an elaboration upon or an explanation, please ask.
So you're writing it as a block diagonal, so each block will be the same matrix?
Not the same matrix. These alphas would change in value. So this is, for example, 1, 1, 2, 1, 3, 1, 4, 1. There would be others like 5, 1, 6, 1.
Can you go back?
Sure. There you go.
So these alphas
Yes.
were defined as the action. Oh, that was only on one space.
Yep.
Okay. So for each space, subspace, you will have different groups.
Yes. So the actual shape that you get once you apply this on this is you get this entire, what you have, these V1, V5, and so on until the last one and lined up in the right order. And then you have, for example, a 16, 16 matrix with 4, 4 diagonal blocks. So all of these are 4, 4 diagonal blocks. This is what you would get. And each diagonal would look something similar to this. I mean, the values would be different, but it would be a clubbing of a 4 cross 4 diagonal block. Okay, contrast it with the case where these vectors, these V1 to V16 vectors are indeed eigenvectors of the operator. So the operator is C. If C applies on V1, it reports a constant scaling times V1, and of course this constant scaling, it's customary in numerics to write it with a tilde on top. So if the representation is C of the operator, then the symbol representing its eigen symbol or eigenvalue is written with a quidl on top. Okay, so this one is rather simple. Can anybody tell me here, if I were to do the exact same thing and I wish to find, instead of this, if I wish to find C times E, where E is again constituted from those 4, E1, E2, E3, E4, but since C has the basis vectors as eigenvectors, how would this transform? You would again have those first component, first matrix. The second matrix would again be a 16 cross 16 matrix with just like this. It would be a simple diagonal matrix. In that case, it would be a block diagonal matrix where each block is 4 cross 4 because of the invariance, exploiting the invariance property. All right, so this is what you see. The amplification of E is defined by a block matrix with 4, 4 diagonal blocks. So the amplification factors are the eigenvalues of the 4, 4 blocks. Does it look like I made another typo on this slide? So read closely. The text says the amplification of E, mind you, E, not X, is defined by a block diagonal matrix with 4, 4 diagonal blocks, and so the amplification factor are eigenvalues of those 4, 4 blocks. In fact, all you have to do instead of finding out, so imagine there was neither invariance nor eigen function property. What would then this look like? What do you think? A 16, 16 dense matrix, a monolithic matrix. 16 is a very humble example, by the way. It could be pretty much, it could run in billions. And then an eigenvalue problem is more or less inverting an eigenvalue problem is of the same big O as solving the original problem. So there's no point if you have to do it all together, because you can't do it. All right, so we can already do away कि ये कितनी भी बड़ी हो, however large this matrix is, any order, you would always have these 4 blocks coupled together in this fashion. Okay, so there is no typo. It is A times C or A into C, which means that you have first this matrix with 4 diagonal blocks, and then that matrix which has those diagonals. So each of these 4 blocks, each column, 4 columns, it gets scaled with those 4 eigenvalues right here, okay, on this one. All right, so I hope that this is a bit clear. And now we go on to regress Fourier analysis preliminaries. All right, the first thing to show up is the bivariate Fourier modes. They are eigenfunctions, are they? Bivariate Fourier modes, Fourier sine modes to be precise, they look like that. Fourier analysis using the bivariate Fourier sine modes is completely rigorous for 2D Laplacian based operator with nice properties. What nice properties? Constant coefficients, Dirichlet boundary conditions. Using this, you discretize and you find that these are the actual eigenvectors of the matrix you obtain. Okay, now this is kind of a big help. Why is this a big help? Because otherwise you'd have to find the eigenvectors of the matrix, of the entire matrix, which is again big trouble. So what we've done here, what I don't show you, but I can still talk about it, is that I have the PDE operator with Dirichlet conditions. I construct a continuum characteristic value problem. I solve it using breaking up the PDE into multiples of ODEs. I find out the characteristics, and I discretize the characteristics. I cheat upon them. I discretize the characteristics. Once I have the discretized version of the characteristics, I apply them to the discrete operator just to check out if my suspicion is correct. And indeed, I see that they are the eigenfunctions of the discrete operator, the discretized version of the continuous characteristics. So this is the route I take. This is how I know that bivariate Fourier modes are the quantities I need to, tweak. Okay. So the discrete operator AH as well as the smoothing operator SH of classical omega Jacobi have these sine modes as their eigenfunctions. Later on in the next lecture, the first thing we would leverage this point to make a case for local Fourier analysis, which is not rigorous for Dirichlet conditions. But we certainly have a point, because if we have other smoothing methods like Gauss-Seidel, Gauss-Seidel red-black, omega red-black Jacobi, SSOR, for example, then these bivariate Fourier modes, they are no longer the eigenfunctions of the smoothing operator, but they still resemble the local exponential Fourier modes quite well. Okay, so this is one of the things that I have in mind for making a case for local Fourier analysis. The scope of local Fourier analysis for analyzing multigrid methods is much more greater than what could be done in such a stringent rigorous way. But this is absolutely rigorous. Yes?
So if you solve in a problem where you have non-homogeneous terms.
Yes.
So
non-homogeneous as in? So
like you have Laplacian, and then on the right hand side you have some function.
All right, sure.
So these Fourier modes in your algorithm, these will still be the relevant Fourier modes, and they will.
If you have Dirichlet conditions, yes, and the negative Laplacian.
So they will do the job.
Yes, of analysis, of analyzing. I just have to use them for analysis. They have nothing to do in an actual solve. Mm-hmm. I just start with a random vector, an all zero vector, a random guess. I feed it to the 2-grid engine, and it spits out an approximation. Okay, it's like that. Okay, so there's a bit more about these Fourier modes. These Fourier modes, in these Fourier modes, KL, they range from 1 to n minus 1, and the I and the J, they basically show up. So initially it was something like this. So these Fourier modes were initially like this, where you had sine k pi xh, sine l pi yh, but this xh could be written down as I times h, and similarly this could be written down, say, as j times h, and h could be written out as 1 by n. So this is how the Fourier, the bivariate Fourier modes with which you are accustomed to see those, they translate into these L pi j over n. And then these I and j are in this range, k and L are in that range as well. How do we construct, so a small hint at how do we construct an actual vector just for the analysis purpose. We fix the KL pair. That is what we do not change in one single instance of a vector. So the KL pair is fixed. However, I and j run from these values, so n minus 1 square combinations, and n minus 1 square elements all in all. So the span of this for a given KL pair for all k and l, so this part is missing. एक चीज़ यहाँ पे, so this part is missing. For all KL, the span of this is basically this. So the corresponding eigensymbols is a fancy word which is relevant perhaps only in numerical linear algebra or in the multigrid community. It simply means formal eigenvalues of the operators. So the symbols of the discrete 2D negative Laplacian operator, which I represent like this, is this quantity. Okay? And though it would be a bit of an afternoon's job working them out, it's rather straightforward an exercise in trigonometry, that's it. Okay. Now something important and often underestimated when you are out reading multigrid literature. Fourier analysis of both kinds, it essentially depends on a partitioning of Fourier modes into two categories, a high frequency mode and a high frequency modes and low frequency modes. And this basic definition or this basic partitioning of high and low frequency, it basically depends intrinsically on the grid coarsening scheme which formulates the coarse grid. For example, if you have a fine grid and you do a mesh doubling, then you know that the low frequency vectors or low frequency components are all of those where k and l both are restricted to n by 2 minus 1. If k and l are restricted to this, both of them, then only you say that a mode is low frequency. Okay, if you have a coarsening scheme, say, where you do a mesh tripling instead of mesh doubling, which is what Shahid Ashraf did for his MS thesis back in 2014, there you have to alter the definition first of this partitioning, the high frequencies versus the low frequencies. So there the ratio would be 1/3 per dimension. Here it's 1/2 per dimension. So this is a subtle point which needs to be understood, that definition of or partitioning of the Fourier modes into two sets, a high frequency set and a low frequency set, is not arbitrary or haywire. It has to follow, for a rigorous analysis, it must follow your coarsening scheme, the coarsening scheme that you're using in your two-grid method.
But you must be using some arbitrary criteria to say that I'm calling this low frequency. Or is there a reason that you say that if I double, I'm just going to call the half one as low frequency?
Yeah, the criteria is, so a lot of this is borrowed from legacy, and legacy analysis was done on this fruit fly problem, which is the Poisson problem, one-dimensional Poisson problem. We've seen one-dimensional Fourier modes in the last class. And whenever we have a Fourier mode with frequency ranging from n by 2 to n minus 1, and we run Jacobi on it, it damps the mode out like anything. However, if those are the initial first few frequencies, 1 to n by 2 minus 1, those modes are kind of persistent or resistant to Jacobi. They don't get damped easily. There's very little damping that happens per iteration. Right, so your question is actually much more deeper than the scope of these lectures. When we're done with the entire bit of multigrid, how it works, how it's analyzed, how it's applied to different challenging problems, the remedies that you have in place, the preconditioning, and all of it, then you still realize that this initial step of what to call a high frequency and what to call a low frequency is still kind of elusive. This gives way to an entire new regimen of multigrid methods, which is called AMG, algebraic multigrid. So algebraic multigrid, algebraic multigridders, how do they define high frequencies? They say, just run Gauss-Seidel on your problem once. Whatever gets eliminated is high frequency, whatever persists is low frequency. So they have a very clear definition just based on the norms. And being rigorous mathematicians yourself, you might find this more appealing from an algebraic way. However, let me assure you that these methods, in contrast, are called geometric multigrid methods, because they use geometric information in averaging, prolongation, and many other things. But let me assure you that a badly converging geometric multigrid method is still faster than an good, nicely convergent algebraic multigrid method, because a lot of looking at the matrix is required in algebraic multigrid to see the connections. Makes it theoretically, mathematically optimal, yet practically lot slower than geometric methods. Okay, so frequency has to be partitioned into two sets. High frequency and low frequency Fourier modes. So this is not completely arbitrary, let me assure you of that, but it's borrowed from legacy, and the legacy says that if k and l, they belong to n by 2 to n minus 1 in this set, then this is a high frequency. If k and l, any one of these, anyone, not both, anyone belongs to that set, it's a high frequency mode. If both of them are within that range, then only you say that the mode is a low frequency mode.
High and low frequencies also depends on your coarsening scheme. If
Right.
you take a different coarsening scheme, then the
Yes.
definition is changed
Sure.
in this scenario also.
What do you mean in this scenario? So with standard coarsening,
Scenario of algebraic multigrid, not talking about
yeah.
in the scenario of geometric multigrid.
Yes, it does. If you have a grid tripling scheme, mesh size tripling scheme instead of the standard coarsening, it would alter. So then you would have n by 3 to n minus 1 or something of that sort if you triple the mesh points instead of doubling them in each go. Is that what you mean?
Yes.
Yeah. Yeah.
So the mixed mode, you will still call them high frequency, or because the way you have defined their other
Yes.
modes?
Yes. So if this is, for example, the frequency block. Let's see if this is not the spatial, but the k-axis and the l-axis, then everything inside here is low, everything here is high. Okay? In 2D. So 2D, the ratio is 1/4 to 3/4, but in 1D, it's just half. A few more symbols. We already know smoothing operator, omega Jacobi, simple case. Eigenmodes of SH are these Fourier modes. Eigensymbols of SH are evaluated, well, we evaluate them to be these quantities. And since those are eigenmodes of the omega Jacobi method, we need not be a lot worried, because we know that at the end of the day, they would just translate into a diagonal matrix. How do we define the smoothing factor? There's a very important quantity, a baseline for smoothers. Smoothers are classical methods like Jacobi, Gauss-Seidel, etc. So the smoothing factor is defined as mu, and this uses whenever you see a relaxation parameter, whenever a relaxation parameter is absent, a smoothing factor is easier to visualize if it's not there. If the eigenvalue expression or the eigensymbol expression is completely devoid of omega, it's easier to imagine what's happening. It's the largest absolute eigenvalue, not in the entire frequency region, but only in the high frequency region. So the largest eigenvalue of the smoother, if KL, which appear in the expression, belong to the high frequency Fourier region, you say that whatever that quantity is, the max of it is the smoothing factor. It's the worst case with which your high frequency vectors are smoothed out per iteration. Okay, it's a worst case. Now, we immediately realize that there is some room to optimize it even further using an independent parameter. So omega Jacobi and SOR just use one, it's omega. In AOR type of methods, they use 2, omega and gamma, and so on. So there is a function, it is also a function of omega. Now think of it this way, it's easier to think what's going on. Before I tell you exactly what's going on, this is known as the minimax criterion. Now what is happening here? If you fix omega and you find the worst case here by examining all of these, now you have a finite range. A good thing about rigorous analysis is that you have a finite range of frequencies, where you have discrete frequencies, discretely many and finite. How else the world could get any better? So you examine all of them in a computer program, you check out, you say, fine, this is the guy we've picked, this is the largest. But it still has an omega that you've substituted inside. Now the guideline for omega Jacobi for most nicely elliptic problems is that omega has to stay in this range. You chop up this line 0 to 2, make thousands of pieces, not thousands, hundreds would do. So, because these are not so sensitive, these are just sine functions. So you examine the largest, you examine the max for each omega, you have chopped up the omega into hundreds of pieces, you examine it for each discrete omega, and then you have many maximums. The maximum, which is the smallest, is the smoothing factor of omega Jacobi, and the responsible omega is known as the optimal omega, optimal relaxation parameter. And this is why it's called relaxation. It relaxes the high frequencies, makes them smooth. Okay, discrete eigenfunctions of AH and A2H. We already know that these Fourier sine modes are discrete eigenfunctions of AH as well as its inverse, and if you were to restrict KL in this range, then these are known as phi sub 2h with KL restricted to this range, and they are the discrete eigenfunctions of A2H and A2H inverse. So no trouble coming in from here either. Then you have a definition of the harmonics. So you now say that you've restricted KL to 1 to n by 2 minus 1, and these 4 functions, you club them with a certain rule. So you have a KL pair, pick a KL pair belonging to the low frequency region, and then construct 3 more with this rule: phi h n minus k n minus l, and phi h n minus kl, phi h k n minus l. And then do a bit of an exercise in trigonometry to see that if you restrict these to this regime, where each of these has an I times h and a j times h, and I and j are both even, essentially even, because we are talking of hierarchical grids. A coarse grid, which is a subset of the fine grid. We are not talking of that case where the coarse grid points are not a subset of the fine grid points. So we are talking of 2 hierarchical grids, 2 grids which are hierarchical. Okay, so you can check that up to the sign, there is a sign difference, but they all coincide, these 4 coincide and become this on the coarse grid. They coincide with the, otherwise on the fine grid they are linearly independent. Okay, these are called harmonics in this context. Yeah, so you can already spy, right? So I gave you linear algebra primer, short one. I dared to give it to you guys. But what you saw are that there you get 4 matrices which would let you analyze the amplification of modes. And I'm building a case on that. Spaces of harmonics. I call it E sub h super KL. We now define the 4-dimensional spaces of harmonics as the span of these 4. So these are always 4-dimensional. And EH, KL is the span of them. And if in this one we've said that KL would belong to n by 2 minus 1, but if it were to become n by 2, what would happen? Because of the periodicity, you would get, they would merge, and what you would get is a 2-dimensional or a 1-dimensional space instead of a 4-dimensional space. All right, so this is the full weighted restriction operator. A full weighted restriction operator, what does it do? And what kind of a linear transformation is it? It is mapping a 4-dimensional space to a 1-dimensional space. The 4-dimensional space is what I just showed you, and that is the span of just one vector on the coarse grid with which it aliases on the, all 4 of them alias with that. All right, so when I apply the restriction operator to these product of sign modes at the end of the day, don't forget. Okay, so one of the cruel things out there is there's so much symbolism here that people who are exposed to it the first time, say in a lecture of this sort, they tend to forget what everything stands for. Okay, so these are nothing but product of sign modes. And this is nothing but a 16-point averaging, a 16-point stencil. Yeah, so I can show you what the stencil is like. This stencil has the form. So IH to 2H, where this is full weighting of order 2, this is the name of an averaging scheme, is just this averaging operator. You have a 4 in the middle, 2 on the sides, and 1's on the corner. So they all sum up to 1. And since you are going to average out the residual, I have to divide it by 16 to ensure that I get no bias in the norm. I don't want to, I don't want to mess up with the norm.
So this is a linear transformation from one space to another, or what?
This is exactly the IH to 2H there.
So then why is it a 3 by 3?
This is not a matrix, okay? It's a stencil, it's a molecule. So this is applied to, say, a grid of this kind. So let me tell you exactly what's happening here. So you have a grid. Yeah, let's say a grid with 16 cells per dimension, or maybe 8 cells per dimension would do. What you want is now to average the information that you have onto these points. So the scheme is mesh doubling. All the unknowns, all these unknowns, they're 49 in number, all these unknowns belong to the fine grid, but only the yellow crosses belong to the coarse grid. So in order to average the information here, that formula tells me that the existing value at this position is to be multiplied by 1 by 4. These two have to be multiplied with, these 4 have to be multiplied with 1 by 8, and these 4 by 1 by 16, and then everything has to be summed up and placed here. This is what that molecule means. Okay? So the restriction is a linear transformation which takes a 4-dimensional span, maps it into a 1-dimensional span. And when you check out its action on the Fourier sine modes, what you see is that when you apply it to this one, you get this constant out times this. When you apply this, for lack of other suitable words, on this sine product of sine modes, you get this constant times this, and so on. So what we call these constants is this. So these constants are called I h to 2h cap. I can put a super KL there. I h to 2h cap n minus k, n minus L. This guy is this. Similarly, I can name the other two. I call these symbols. These are not eigenvalues. I just call them Fourier symbols. I don't call them eigen symbols. They are not eigenvalues at all. Eigenvalues are concepts related to operators, not to general linear transformations. So these are merely symbols of the restriction operator. And again, I can load you, if you happen to become a victim in one of my classes, I can load you with the calculating these. I mean, this is a simple operator, the one that I wrote above. Yeah, that one. But I can have full weighting of order 3, I can have full weighting of order 5, I can have all the terrible sorts of restriction operators. Maybe each restriction operator, the entire molecule has 25 or 49 or 63 elements. And you can do a trigonometry exercise by hand, or you could employ something like Maple, for example, and come up with a symbolic crunching of those trigonometric expressions and get to the symbols. But the symbols are there. and the symbols will come out. And the restriction operator maps EHKL to span phi sub 2H KL. Then I have bilinear prolongation, the reverse procedure, the interpolation. There also I have to preserve the row sums. Again, why do I need to preserve the row sums? If I don't preserve the row sums, I would get a bias of the vector that I am calculating, which is not what I want. Okay, so what does this do? It does exactly the opposite. So it maps a one-dimensional space to that four-dimensional space. And this is what I get. This is what I always get. So if I apply prolongation to this, if I apply bilinear interpolation, full weighting of order 2 has an adjoint which is called bilinear interpolation. Bilinear interpolation for structured grids could be represented with molecules of that sort, with outgoing molecules. There is a bit of, what's the right word for it in English? There's a bit of a frustration how to represent outward molecules. So inward molecules are simple. These are inward molecules represented by this one. In some books, they write this for outward molecules for bilinear prolongation. Sometimes they write them like this, and this gets ever more confusing. But at the end of the day, you need to know what is bilinear interpolation. Bilinear interpolation is a simple interpolation. It's linear interpolation in 2D, which is exact for linear functions per dimension, or bilinear interpolation is exact for bilinear functions. If the underlying missing function is bilinear, using bilinear interpolation would lead you to the exact values. All right, so when you apply this to the lone mode you have in this space, to the lone basis mode, you get an expansion of this sort. Okay. So these are the symbols of, now you can argue, is this a coincidence that the modes, that the symbols of restriction and the symbols of this prolongation are exactly identical? What do you say?
Yeah, probably everything the points which are around it in the course grid, right, in the final point.
So come again.
So if you have a point on the final grid which is not on the course one, you're somehow averaging the ones which are around.
Yeah.
And that's probably.
Yes, and what I seem to have forgotten is if you have a higher order interpolation and its adjoint as restriction, do they share the same modes in hierarchical grids? They do? Bicubic interpolation and full weighting of order 3, the symbols are the same? Okay. They're basically adjoints of each other. So in matrix terms, if you were to create using that formula, the formula that I just wrote with the inward brackets, if you were to create a matrix, say if this molecule is represented by IH to 2H, and you say, fine, I have now applied this to each grid point, and I have a matrix R, what would be the order of this matrix? Dimension क्या होगा इसका? It has to multiply with a long 49 cross 1 vector, create a 9 cross 1 vector naturally. So it has to be 9 cross 49. So if I have a restriction operator or a restriction matrix of this sort, then the prolongation matrix is just its transpose with a scaling that ensures that the row sums are 1. Okay, now the fundamental thing. We asserted in the beginning that the coarse grid correction operator is invariant, or these spaces are invariant under the coarse grid correction operator kh to 2h. Now we can show it. How can we show it? We are saying this takes span this into span this. The two spaces are the same. However, this maps this into this. Then this maps the same thing into the same thing. Finally, this maps this to this. So what basically happens? The two vector spaces turn out to be the same and invariance is conserved. Okay, so if invariance is conserved, we've already seen this, each one of these independently, the last few slides. So if independence is conserved, what actually do we get as the structure of the amplification? Yeah. So what we have are the symbols of K represented by K hat, KL, in which these are 4 cross 4, respectively 2 cross 2 or 1 cross 1 matrices when one of them or both of them equal n by 2. But when they don't, you get 4 cross 4 dense blocks. And it wouldn't matter. So SH is kind of, a non-important guy in this, an important and yet a non-important guy. So an important guy because if you don't place it at the ends, you don't get a convergent two-grid method. So it's very important. But from the analysis viewpoint, it doesn't impact the difficulty of analysis in any negative way because all it induces is a diagonal matrix which gets multiplied to the left and the right of the coarse grid correction operator. Okay, so the spaces are also invariant under the smoothing operator employed in two-grid algorithm. This is trivial for omega Jacobi smoothing. And for omega red-black Jacobi, the two-dimensional subspaces, these two-dimensional subspaces and the degenerate one-dimensional subspace are invariant under the omega red-black Jacobi operator. But haven't described the omega red-black Jacobi process yet, but this is an important addition. So MH to 2H representation with respect to these spaces. Again, we have the exact same thing that we had with KH to 2H. The only thing there was that the symbols of KH to 2H could be larger than 1, but the symbols of MH to 2H abounded by 1, making it into a convergent algorithm. Okay, now, fine. We got the broken bits you hammered in our heads. What are we supposed to do with it? We're supposed to, so this is we are supposed to write a computer program. What would that computer program do? The computer program would walk on all the available ordered pairs in this entire regime, in this entire low frequency part. It will pick one, ek uthaya, it will pick one, then would do what? Construct 3 of its brothers in this region, n minus k, n minus l, don't forget that, n minus thing. This is n minus k, n minus l, the others are these two. Once it has these 4, then you have all the quantities that you need. All you got to inject them are in the 4 cross 4 representation for MH to 2H cap, the symbols of MH to 2H. Okay, so let's suppose you have a very fine resolution in your program. You wish to do a rigorous analysis for it. You have, say, 512, n is equal to 512 here and here. And you would get many such points. For each of those points, you would construct Again, reiterating, a KL in the low frequency region, come up with 3 KLs in the high frequency region. As soon as you have that, you have the value of MH to 2H for that KL, for that initial KL that you used. What do we do with it? And which value is it exactly? So it was a 4x4 block, don't forget. Okay, don't let it fade out. It was a 4x4 block. You have not one frequency, but 4 frequencies. What do I mean by putting a row over it? By that I mean that for that 4x4 block, you would get 4 eigenvalues and you got to pick the largest one, the maximum. You store it in a vector. You pick the other one, construct 3 more, repeat the process, get a set of 4 eigenvalues, easy peasy to compute, super easy to compute, just a 4x4 matrix. A humble size by any standard. हाथ से भी कर सकते हैं, हाथ से नहीं कर सकते. We need a computer program for it. उसका maximum फिर से store कर लिया. You store all of the maximums और इनका जो max है, a max of the maximums, ये basically आपका 2-grid convergence factor है. और अगर आपने सारे components, if you have used all the components, all the right components in a good convergent multigrid algorithm, your 2-grid convergence factor would be close to 0 and away from 1. It's not just that since it's convergent, it has to be less than 1, so let's have it 0.1,000,009. No, that's not what it's meant. It certainly has to be less than 0.5. Anything, the two of you, anything that has a convergence factor over 0.5 needs correction, period. There is some component that's malfunctioning. Okay? So the factor 2-grid convergence factor has to stay less than 0.5. If it's 0.1, what does it mean, Samreen? 0.1. Yeah, but what would it mean beyond that good? Practically speaking. 2-grid convergence.
If the convergence factor is 0.1,
Yes.
what would that mean?
Yeah.
ये एक step answer देते हैं.
No. Depends on your tolerance, right? If you say the relative residual has to reduce 6 orders of magnitude, then 0.1 means 10%. एक digit कम हो रहा है beyond the radix point. So it would conclude in 6 steps. If your tolerance you've asked for is 10 to the power negative 10, for example, it needs 10 cycles or 10 iterations. This is the meaning of a convergence factor of a 2-grid method being 0.1. Okay, 0.5 का मतलब है आधा हो रहा है. That's it. That's it for today. I don't know if 2 hours have gone by or not. Hardly. So, yeah, any questions? Yeah.
So one of the questions about your very last statement. So if it's like so efficient,
It's not always so efficient. It's a glorified picture. So there are many caveats here.
okay. No, I mean then even like 0.5 is not a big deal because
not a
it looks like it's like exponential because with each iteration you're reducing it by a factor. So if 0.1 with 0.1, I mean you need 10 steps. Having I don't know, I mean 20 steps, is it too big of a thing?
No,
Is it
10
big?
steps is wonderful. 10 steps is
Going
optimal.
from 10 to 20, does it cost a lot of computational power?
No, 10, 20 is also tolerable, but anything that runs into 50 iterations or 100 iterations, अब कितनी 500 आ रही हैं, कितनी आ रही हैं? So if you have, even if it's a convergent method but has a bad convergence rate, convergence rate doesn't always stay constant. So sometimes if the method has components that have an underlying fault that needs correction and has gone uncorrected, then the convergence factor from iteration to iteration doesn't always stay in a sequence.
Okay.
it's not the same convergence factor. In the first few iterations, there's rapid decrease, then the decrease stalls, and that happens.
Sometimes it also happen that the cycle becomes so costly, it will overrun CPU time.
Oh yes. So if you have a reduction that is too bad, for example, you choose not to have hierarchical grids, for example, but you want 90% grid retention on the coarse level. So if your coarse grid is constructed of 90% of the variables on the fine grid, then it's not good grade reduction of the grid. So even if you do a fantastic job at eliminating the little bit of frequencies, high frequencies that you have in your fist, it would cost a great deal because then you have a lot of cycles. Here, if you have mesh doubling, the cycles go down by a power of 2. 128, 64, 32, 16, 8, I exactly invert on 8. So I just have 5 grids. But if I have 128, 108, 100, 90, 80, 60, 50, 40, 20, 10, I have 10 grids. So smoothing would definitely become good because now you have just a few high frequencies which you can target to obtain your optimal omega, but the transfers, grid transfers would dominate in the work that's being done, which is why I say that an estimate of the work is really required to understand what's going on. Anything else?
Some interesting coarsening scheme is 0.2/3.
Yeah. So when we do advances and challenges, we'll discuss for sure the problem that you're tackling. So the problem that Zulfikar is tackling has a very weird spectrum. That spectrum has artifacts which render it nearly non-edible by multigrid. Nearly is the word. It has some eigenvalues which are extremely large and some eigenvalues which are literally hugging 0, which means that the discrete problem is nearly singular, and we have only 15 digits of precision in double precision computing. I've tried many remedies, nothing has worked so far other than bad reduction of grid, but we're still on to the problem. Some preconditioning might help though. Okay, that's it. Thank you.